We are going to be talking about balancing chemical equations today. And I alluded in previous lectures that this was coming, so I am pumped because I love this part. It's just refreshing to see a balanced equation. So when we write a chemical equation, the number of atoms of each element must, exclamation points, must be the same on both sides of the arrow because we cannot create or destroy matter. That's our conservation of mass, or our conservation of matter. Now, there's a few videos that are helpful to watch. Feel free to watch them. But I just kind of want to show you what this looks like because it's kind of hard to grasp if you go, well, wait a second, on the left side here I have water, on the right side I don't have water, so how am I conserving mass? Well, what we're going to do, and I'm going to show you how I like to do it. I like to divide my reactants from my products. So I've got my reactants on the left, my products on the right, and then I like to make a list of what do I have on the left. So notice that I have this SO3, sulfur trioxide. So we can see that I have 1 sulfur and 3 oxygens. So I'm going to write down 1 sulfur, 3 oxygens, and then I look right here and I have a water. So notice I have 2 H's, 2 hydrogens, and there is another oxygen. So I've got this, it's signified with a red ball here. I've got a red ball, but over here I had 3 reds. So I have a total of 4 reds, or 4 oxygens. So I'm going to do 3 O's plus 1, so I have 4 oxygens. All right, and then, so these two combine to form, so this is our synthesis reaction or our combination reaction that we talked about in the previous lecture. On the right, I have H2SO4, I have sulfuric acid. And so I only have 1 product. So let's see what's in that 1 product. I have 2 H's. I'm going to line them up down here so it's just easier to compare. I have 2 H's, I have 1 sulfur, and I have 4 oxygens. So just by looking at this list, we can see that we have 1S, 1S, 4 oxygens, 4 oxygens, 2 hydrogens, 2 hydrogens. We can see that we have the same number of atoms, but just to show you that we're following the law of conservation of mass, let's look at the actual masses. So if you grab your periodic table, we can see that sulfur has, and I'm going to do just some rounding. We're not going to use the 3 decimal point on these just because I want to just roughly show you that the mass is equivalent. So the mass of sulfur shows us on the periodic table is 32.066 or 32.07. So I'm going to write down over here that we have the mass is 32. We're going to round that, and we're going to times that by 1 sulfur. 4 oxygens. So we're going to show that we're going to take 4 times oxygen is 15.99. We're going to round that to 16. So 4 oxygens and 2 hydrogens. Hydrogen is mine says 1.0079 or 1.01. We're just going to round that to 1 for the purpose of this. So we've got 32 plus 64 plus 2, which is 98, a mass of 98 AMUs, or atomic mass units, or now I think they dropped that AM, so now it's just 98 U for atomic mass units. Okay, so that's what my left side weighs, right? Now, if I were to do the same thing over here, we would see that, all right, if I have 1 sulfur, each sulfur is 32, 4 oxygens, so each oxygen weighs 16, 2 hydrogens, each hydrogen is 1, and again, if we would get the same as on the right, on the left, right? We would have 98 atomic mass units. So notice that these two match. So the left side is equal to the right side as far as mass. Now here's a quick video I want to show you to illustrate also with a real chemical reaction since we're not in the lab to see this. All right, so we're showing that matter cannot be created or destroyed. So we have our scale here, and we have a flask with chemical in the flask and chemical in the test tube. So total, we have a starting mass of 158.2 grams. Now that's everything included. Now when we mix this, we can see that there is a chemical reaction that just happened. Not only did we have a change of color, but we also have a precipitate form. So we have the solid. Okay, chemical reaction just occurred. When this, yeah, there we go. When we put it back on the scale, notice its final mass is 158.2. We did not gain mass, we did not lose mass, but we have different final products than what we are starting with. Now this shows us that our initial, so here's our reactants. We started with aqueous lead nitrate and aqueous potassium iodide. We had two clear liquids that were aqueous solutions, and when we mixed and combined them, we got aqueous potassium nitrate and our solid lead iodide. We can see here that I have different products than my reactants. However, because of a balanced equation, I can see here that I have two potassiums on the left. I had to balance it so that I have two potassium iodides, so two Ks here. And on the right, I have two Ks. On the right, I have two nitrates, NO3s, because on the left, I have two NO3s. I have one Pb on the left, one Pb on the right. I have two iodines on the right, therefore when I go over to the left, I have two iodines. Now we're going to look at this example of a reaction here. We have methane gas, so CH4, plus ammonia gas, so these are my reactants, and they combine to create, I'm going to draw a line in between. Wherever there's an arrow, I like to draw a line. I like to separate my reactants from my products. We get HCN gas and hydrogen gas. Okay, so I like to make a list of what I have. So I have one carbon, I have four H's, I have one nitrogen, and I have three H's. So I'm going to add that together. So I have a total of 7 hydrogen. On my right side, I have one H plus one carbon plus one nitrogen plus 2 H's. So we have 3 H's. All right, now let's look. Are we balanced? Well, I've got one carbon, one carbon. One nitrogen, one nitrogen. Those are all good. But notice that I have 7 H's over here and 3 H's over here. Those do not match. So I need more hydrogen. So let's look at what we can do. This is where the coefficients come in. If I were to add more hydrogens. Now, there's two different spots where I can add hydrogens because there's hydrogens in this product and there's hydrogens in this product. If I were to put a coefficient of, let's say, 3 right here in front of this, sure, that's going to give me more H's, but it's also going to give me more carbons and nitrogens, and I don't really need more carbons and nitrogens right now. So I'm just going to add more H's where H is so low. What would happen if I were to give me more H's and put a 2 there? That would mean that I would have 2 H2. So instead of, this is 1 H2. So what if I were to add another H2? So that this would show me 1 H2. This is 2 H2s. So I would have 1 hydrogen there, and then 1, 2, 3, 4 over here. So 4 plus 1 is 5. Would 5 H's on the right give me a balanced equation? No, because the left side has 7. So let's go back. Sometimes balancing the equation makes us have to go back and erase, and that's okay. So now let's try, instead, if 2 didn't work, let's try 3 H's. So I've got 1 H2, 2 H2s. Let's do another H2. So 3 H2s. That would give me 1, 2, 3, 4, 5, 6. And plus that 1 is 7 H's. 7 H's. So then, cross this off. Now that we have those 3 H2s, we now have 7 H's, which balances my equation. So here's a YouTube video that's also nice and helpful if you want to check it out. But just to kind of show you what we just did, we added a coefficient in the chemical formula, which is a multiplier, right? And we put it in front of a substance that is deficient, that's lacking, so that we can have more of that in order to help balance. We never change the subscripts. Never, never, never. The subscripts would be like this last one where I had H2. I can't all of a sudden go, oh, I need more H's. I'm going to make that H7. No, 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 no. Cannot do that. So we cannot change the subscript. That is a big no-no. It can't happen. It would be like if I said I have H2O, I have water, and I needed more H's. I'm going to make that H7O. Well, then it's not water. So you are totally changing the compound when you're doing that. But if I were to say I wanted 3 waters or 5 waters or whatever the case may be, then that's how you need to do it. You need to do it by changing that coefficient. So a couple of rules to live by. 1, check that the chemical formulas are correct. Like, for example, if I were to say lithium chloride added to water, if you wrote LiCl2 plus H3O, this would be wrong, and we were not going to be able to balance it correctly because, first of all, H3O is not water. Water is H2O. So that changes how many hydrogens I would be trying to balance. And lithium chloride, we know that this is incorrect because lithium is always a +1 cation and chlorine is a -1 anion. So this compound would be 1 lithium and 1 chlorine, not LiCl2. So this would be incorrect. We need to write our chemical formulas correctly. Then when we get to the point of adding those coefficients, sometimes it takes a little bit of time, like you saw when we were like, oh, maybe let's try 2. Oh, maybe let's try a 3. It's okay if that takes you a minute. Coefficients must be whole numbers. To try to get to 7, I can't say I need 2.5 waters. They only go in full whole numbers. And then always double check. So let's look at this example of hydrogen gas plus oxygen gas, which combine to give me liquid water. So I'm going to draw a line here, and I'm going to go, okay, I have H's and I have O's. And over on the right, I have H's and O's. How many H's are here? I have 2. How many O's? I have 2. 2 O's. How many H's on the right? I have 2. How many O's? I have 1. So then let's go and compare and see. Okay, yep, 2 H's, 2 H's. Good. Oh, this has 2 O's. This one only has 1 O. So I need more O's on the right. So I need to add a coefficient on the right to give me more. So let's do this. Let's say, okay, let's have 2 waters. Now, if I have 2 waters, that means I have H2O, H2O. So this 2 affects my H's and my O's. Make sure that that distributes. So I now have a total of 4 H's and 2 O's. Yep. Sometimes when you do this and you only want more O's, sometimes you get more of another, and that's okay. So now if we look, my O's are good. Yes. but my H's are now goofed up because I have 4 H's on the right and only 2 on the left. So I need more H's on the left. So if I have 2 H's, to get to 4 H's, let's just put a 2 right there. So that 2 H2's, so H2 and H2 gives me 4 H's. Now we are balanced. Now I would like for you to pause and try to balance these two chemical reactions. We've got hydrogen gas plus bromine gas to give us hydrogen bromide gas. So this is problem number 1, this is problem number 2. So I would like for you to take a second and try to balance. Let's see how you did. So again, I like to draw my line, separating my reactants from my products. And I like to go, okay, I have hydrogen on the left and bromine on the left. Hydrogen and bromine. And I have hydrogen and bromine. Let's match these guys up. And then I like to say, all right, I've got 2 H's on the left and 2 bromines. And on the right, I have 1 and 1. 1 and 1. So now let's look and see who needs more. Do I need more hydrogens on the left or more hydrogens on the right? I need more on the right. So if you think in multiples, because that's what coefficients do, how do I get from 1 to 2? Well, I would need to multiply by 2. So remember, this now tells me I have 2 HBRs. I have HBr and HBr. So that means I have 2 H's, no longer 1, I have 2, and 2 BRs. So now I have 2 H's, 2 H's, 2 BRs, 2 BRs. Okay, and so my fault, as I was looking at this HBr, I'm going to erase, now that we've got this answer, I'm going to erase this because this drawing is not, I was thinking at first that this drawing was this problem, but it's not. It's its own problem. So we now have 3 different ones to do. So if you want to pause real quick and try to figure this out, we're going to call this, we'll call this H2 plus, we're going to call this N2, and then it combines to create NH3. So there's my 3 H's. So try to solve this one. Let's figure out, we've got how many N's on the left? We have 2. How many H's on the left? We have 2. How many N's on the right? We have 1. H's, we have 3. So by looking at this, we can see that my N's on the right, I only have 1 versus 2. So I need more N's on the right. On the left, I need more H's. So let's start, I like to go top down. So I'm going to show you my line of thinking. I'm going to go, okay, I need more N's on the right. And I need to have 2 N's. So let's put a 2 in front of my NH3. That gives me 2 N's. So I'm going to cross off 1. I have 2 N's. And then remember that 2 distributes. I did have 3 H's here. So 3 times 2 is 6 H's. Now, my N's are good. If I look at 2 N's on the left, 2 N's on the right. But now I need to have 6 H's on the left. 3 times 2 is 6 H's, and now we match. Okay, let's look at our last one that's here. We'll have more, don't worry.
Let's look at this last one. We have aluminum plus bromine, and bromine is diatomic because it's in Brinkelhoff. And it creates aluminum bromide, and it's AlBr3 because we know aluminum forms a +3 cation and bromine is a -1 anion. So that would take 1 aluminum and 3 bromines to have a neutral compound. So we have aluminum and we have bromine. And on the left side I have 1 aluminum and 2 bromines, and on the right side I have 1 aluminum and 3 bromines. So like I said, I like to go top down and we can see my aluminums match, good. And the left side, I need more bromines. So notice the problem though. If I multiply my left side by 2, that would give me 4 bromines, and that's not going to match the right side. So when that's the case, I like to think of what's the least common multiple that they have in common. And in this case, I would like to get to 6, because if I have 2 and I multiply this side by 3, that can give me 6 bromines. And then over on the right side, I can say, ooh, if I multiply this whole thing by 2, that would give me, now it does mess up my aluminums, and that's okay. It gives me 2 aluminums, but then that also gives me 6 bromines. Okay, let's go top down and check. Oh, my aluminums, I need more. I need to match my right side, so that gives me 2 aluminums and 6 bromines on both sides of the equation.
All right. Some more practice. I do want to note this problem and this problem are both on the your turns. First one is not written as the rest of them are. They're in words. So we need to go back and write this equation out in symbol form. And make sure that you're just careful when it says elemental iron. So we need to look at our periodic table, figure out what iron symbol is. Is iron in Brinkelhoff? No, so it's not diatomic. Is iron normally a solid, a liquid, or a gas? Normally a solid. All right, so iron and chlorine gas. Is chlorine just Cl, or is it diatomic? Hint, hint. When we form iron 3 chloride, how do we write that? Remember, think back. What does that 3 represent? How do I write a compound of iron 3 chloride? So that will be on your turn. Let's do this one as a practice problem, though.
For this problem, let's look what we have. We have iron on both sides. We have oxygen. We have hydrogen. And then we have the polyatomic ion, SO4, which is sulfate. And I'm going to keep that together as a unit. And that's something you can do if the same polyatomic ion is on both sides of the equation. And then I also have oxygen and I also have hydrogen. So I'm going to keep that polyatomic ion together. Again, you can do that when that polyatomic ion is on both sides of your arrow. Okay, on the left I have 2 irons, 3 oxygens, 2 H's, and 1 SO4. And on the right I have 2 H's, 1 O, 2 irons, and 3 SO4s. I'm going to go top down, and we can see, let's see here, my irons are good. All right. I need more oxygens on the right. See, I only have 1 and the left side has 3. So I need, where my oxygen is, I need to triple it. Well, that also messes with my H's, which is okay. So 3 times 2 is 6 H's. And then that gives me my 3 O's. Okay, so my irons are good. My oxygens are good. My H's, the left side needs more. We need to triple my left side. So let's do that. 3 times 2 gives me the 6 H's I needed, and it also triples that SO4 sulfate. And now we can see my H's match and my SO4's match, so we have a balanced equation. All right, these last 2 problems, we have aluminum on the left. We have now SO4 is sulfate, and we have that on the left, and we have it on the right, so I'm going to keep it together as a chunk. We also have aluminum. I'm going to just match them up. We have barium on both sides, and we have NO3 is nitrate, and we have that on both sides, so I'm going to leave it together. All right, we have 2 aluminums, 3 sulfates, 1 barium, 2 nitrates. And on the right, 1 aluminum, 3 nitrates, 1 barium, and 1 sulfate. All right, let's start seeing what's not balanced. I need more aluminums on the right because I have 2 on the left. So let's put a 2 in front of where aluminum is. That gives me 2 aluminums. But that also just doubled however many nitrates I had, and I had 3 nitrates. So now I have 6 nitrates. Let's keep going down. So my aluminums are good. I need 3 times as many sulfates on the right as I do on the left. So where my sulfate is, I'm going to put a 3 in front of it. I have to put it in front of the whole compound though. So that messes up my bariums. That gives me 3 bariums and 3 sulfates. All right, so our aluminums are good, our sulfates are good. My barium, I need triple the bariums on the left. So I'm going to triple the compound that has barium in there, giving me 3 bariums. It also just tripled my nitrates, and I had 2 nitrates. 2 times 3 is 6, and that just balanced that chemical reaction. Let's look at this last example here. I have hydrogen. Now I have sulfate again, SO4. Do I have SO4 on the right? I do, so I can keep it together. I also have Na, sodium, and then this is mixed with hydroxide. Is there OH on the right side? Well, remember H2O is the same as HOH. So if you want to keep it together, you can, or we can split it apart. Let's just split it. Since we have H's on the left, we have H's in 2 different spots. So let's just keep the H's split apart. And then we have O and O. It wouldn't matter if you kept the OH together or not. All right, so I have 2 H's here plus 1 H is 3 H's. I have 1 SO4, I have 1 Na, and I have 1 O. Let's look at the right. I have 2 NAs to start with, 1 sulfate, 2 H's, and 1 O. All right. So looking at this top down, we can see here that I have 3 H's and 2 H's. So I know I need more H's on the right. Now, there on the right-hand side, there's only 1 spot where there's H's that I can add. On the left side, there's 2 different spots. So let's just start off by saying, well, what if I had, instead of 1 water, let's say I had 2 waters. That would give me 4 H's and 2 O's. Let's see where that gets us. Well, my H's don't align, but I don't know where I would want to add more. Would I add it in front of Na, or would I add it in front of my H2SO4? So sometimes if you're not quite sure, I skip on and move to the next one. So let's do that. Our SO4s are good, but let's look at our sodiums. Our sodium needs more on the left. We need to double to equal the right side. So let's double where there is sodium. Okay, that gives me 2 NAs. That gives me 2 O's, right? This 2 distributes to all of these guys. 2 O's. And then that gives me 2 H's plus these 2 H's. So that's a total of 4 H's. And just like that, everything balances out. We have 4 H's, 1 sulfate, 2 NAs, and 2 O's.